and we'll get started on this. Now, I've opened the file that's on Blackboard. That's called April 4th, 2016 lab exercise. Okay, there's also another one that's linked to the lecture. I think that is one of the examples that has a couple of examples that Professor Weicker recorded. But this is the lab exercise. Okay, looks something like this. Okay, you can open it up or you can just follow me doing it. Okay, now, first I wanted to mention, when I first started teaching with one of the biostatistics professors in the beginning, we had a very large class that semester. too large that we only had a lab that had like about 15 computers or something like that in it. We had a very, very large group. So we would do a lecture, a 2-hour lecture in a large room. And then students actually paired up on computers and stuff like that. 30 of the students, maybe 60 students would be in a lecture for 2 hours, but they also needed some lab time. So we would do 2 sections of lab. Instead of 60 students in the lab at the same time, we would do 30 in the lab before the lecture and 30 in the lab after the lecture. So half the class wound up seeing the lab before the lecture. The other half wound up seeing the lab after the lecture. And I think to a large degree, the people that saw the lab first sometimes preferred that because we took kind of like a hands-on, apply this stuff approach in the lab, and you actually solve some problems, and then you got to look at the theory. And sometimes that helps, I think. So I'm thinking maybe one of these days we'll play around with that. Who knows? Maybe we'll give that a try or something like that. I'll talk to Professor Weicker. Maybe we'll give that a try and see how that works out. Okay, so at any rate, I'm going to backtrack just on one problem here. I'm going to look at a single sample hypothesis test. Okay, in a single sample hypothesis test, we're going to take a sample from one population and compare it to a known mean. For instance, in this case, I'm going to sample a population. I'm going to randomly select 9 people from the population, and these are the results that I got from 5, 7, 8, 9, 10, 11, 12, 13, 14, and sample size was 9. Now, I'm going to put that into Excel. I will already put the results up here, but I put that into Excel. Here are the same list of numbers. In fact, I think I got one of the numbers wrong. I had a 6 here, and I had to change it to a 5, I think, on the Excel file that I have up here. And I found the mean, I found the standard deviation, and I found the standard error. Now, the standard error is just simply the standard deviation divided by the square root of the sample size. 9, square root of 9 is 3, which is just the standard deviation divided by 3. So roughly, the mean for this population is roughly 10, and the standard error for this sample happens to be about 1. Okay, so now this is a small sample, so we can't think about using the z-score, and we don't know the population standard deviation. Well, wait a second, maybe we do. Maybe in one case, here's why I wrote it twice. Sigma. Okay. Oh, here it is. The first one, I said sigma is equal to 3. It's known, right? If it's known, we can use the z-score. Even though it's small sample size, we can use the z-score. So how would I solve this problem? Well, let's see. The standard deviation is actually known to be 3, right? And that would make the standard error equal to exactly 1. Okay, so now what is my z-score going to be for the difference between the mean of my sample and the mean of the population I'm comparing it to, which is equal to 8? So that would be, I'm going to call it 10, just make it sample. My z-score is going to be equal to x bar minus mu divided by, I'm not going to bother to put the parentheses there for now, divided by the standard error. Or maybe I should, just so that we're clear. Okay, so let's solve that. X bar minus mu, x bar is equal to 9 to 10, and the mean of my population I'm comparing it to is equal to 8. You'll see it there, right? So x bar minus mu is equal to 2. I'm going to put an equal sign here. Divided by the standard error, which happens to be equal to 1. So my z-score is equal to 2. What probability, what p-value goes along with a z-score 2? Well, we know that 2 is greater than 1.96. So the p-score is going to be less than 0.05. I'm going to actually calculate here. I'm going to say it's equal to norm S dist, parentheses, and the z-score is equal to 2, means that the p-value is equal to 0.977, so on and so forth. So actually, that's going to be the value from that point all the way to the left. So really, it's equal to 1 minus that value. Okay, it's equal to 1 minus norm dist. It's equal to 0.0227. But now that p-score is only single-sided, right? We didn't know in the beginning whether we're going to be larger or smaller, so we're really doing a two-sided test. This only accounts for the percentage, the probability of having a result outside that range of 1.96 standard deviations below and above the mean, right? So I really have to double that in order to get my two-tailed standard deviation. Okay, so my overall p-value is equal to 0.045, right? 4.5%. So since my probability of being wrong, if I reject the null hypothesis, is less than 5%, I can go ahead and reject the null hypothesis, right? And accept the alternative hypothesis, that there is a difference in the mean between these two populations. Okay, well, now let's take a look at the situation, single sample t-test, where we don't know what sigma is. We don't know what the population standard deviation is. Well, in that case, we have to use the standard deviation of our sample, which is 2.93. Okay, well, let's see how that changes things. Standard error is equal to this value divided by 3. Okay, which is equal. Oops, I got that wrong. Excuse me. Here's the standard deviation up there. It's equal to the standard deviation divided by 3. Okay, that's 0.997. So my z-score, if I calculate what z is going to be equal to, it's going to be equal to, again, it's going to be equal to 9.988 minus, what was it again, 8, right? Divided by, I should say divided by the standard error, which is equal to 0.97. So I get a z-score of 1.71, except it's not really a z-score, is it? Because I don't know what sigma is in a small sample. That's my t-score. Now, how do I determine if that t-score is big enough for me to reject the null hypothesis? I have to compare it to, the t-score is going to be equal, same way I got the z-score before, except it's going to be a t-score now. It's equal to the value of x bar minus the value of mu, single sample test, right? X bar minus mu over the standard error. How did I get the standard error? The standard error is the standard deviation I got from my numbers, from my 9 numbers, right? Divided by the square root of the sample size, which in other words, the sample size is 9, that would be divided by 3. That gave me my 0.9, my standard error of 0.97815, so on and so forth. I think, right? That should have worked. Yes, I think. Okay, so now my t-score is equal to the difference between the two means, the mean for my sample and the mean for the population I'm comparing it to, divided by the standard error. Okay, and that comes out to be 1 point. Is that right? Does it come out to be? No, it's not. Equals, hang on a second. It's equal to the 9.88 minus 8, right? Parentheses. Maybe I left out the parentheses. Divided by my standard error, which is 0.97, so on and so forth. Comes out to 1.93. Okay, so now that's what my t-score is, right? Well, you know, t-score depends on degrees of freedom. Unlike z-score, we need to know the degrees of freedom to predict what our probability is for t-score. So instead of actually looking it up, instead of actually calculating the p-value, we go to a table that has a chart of t-values. Anybody have one handy that can tell me what t-score for a sample size of 9, 8 degrees of freedom, what value of t do I have to exceed to get a alpha value, a type 1 error value of less than 0.05. I'm going to look one up. T-table at Rusty. That's the one I have on here. Let me see if I can't find it real quickly. Where'd it go? Maybe the other way around. Rusty. There it is. Okay, here's my t-table. So for 8 degrees of freedom, my t-value has to exceed 2.3 to reject my null hypothesis. Did my t-value exceed 2.3? No, it didn't, right? It was only 1.93. Can I reject my null hypothesis? No, you can't, right? Because the alpha error is going to be greater than 0.05. As it happens, because I'm using a table for t, I can only tell that the t value, my alpha is going to be greater than 0.05 or less than 0.05. I don't know exactly what it is. Like I could have calculated somewhat more easily if I had the z-score. So that's, when we use SPSS, that's not going to be a problem. It's actually going to calculate a significance for us using the t-score. So what happened here? What's the difference here? What was the main difference here? The main difference was in one case we knew the population standard deviation. In the other case, we didn't know the population standard deviation, right? So it gave us an advantage to be able to use the z-score instead of the t-score. Okay, so now let's move on to the next version of this that we might have. Okay, and I'm going to show you a chart in a second that's going to help you out with this stuff. 2 sample hypothesis test, assuming equal variances. We don't really know that yet, but we're about to know that. Now here's 2 samples, males and females. We're comparing scores, might be a test score, might be a quiz score, might be who knows what it is. But we're comparing 2 groups, randomly selected groups, the males and females, 9 in each group. And for males equals 9, and for females equals 9. Well, how am I going to analyze this? I'm going to say, for the moment, let me see if I have that this particular 2 sample t-test Excel. Okay, let me blow this up. Okay, I think I got the same problem here. So, no, I got it right. Okay, so these are my males, these are my females. If I want to calculate my mean, okay, I'm going to calculate the mean here, equals average for males, parentheses, is 10, average for females, equals 7.5. My standard deviation for males is equal to 2.7. My standard deviation for females is equal to 1.94. You guys remember what the rule was, a general rule for if we're doing a calculation by hand, for when to decide whether we could assume equal variances or assume unequal variances? Yeah, either 50%, one's 50% of the other, or one is less than double the other, right? So in this case, it's really the same rule, isn't it? It just depends on which one you're looking at, right? Like for instance, right now, 1.94, the other one is not twice what that one would be, 3.8. It would be twice, so it's not twice. And if you look at the 2.7 first, half of that would be 1.4, right? And this one is more than 1.4. It's closer than 50%. So it's really the same rule, right? So I can assume equal variances here, right? Or at least for our purposes. At the moment, I could assume equal variances. Okay, so I'm going to go back here and I'm going to say to myself, okay, so how am I going to handle this now? I have 2 separate samples. What are the rules based on what we just saw in the lecture? What are the formulas that I have to apply here? Well, I kind of summarize them here, if I can ever find it again in this mess of windows. Why does it always want to do updates at the worst possible time? What is happening now? No, I don't need that right now. Thank you. It wants to do a scan. Thanks, but no thanks. Okay. All right, so let me see if I can't find that again. I know I didn't close it. Maybe I moved it down there. Let's see if it's over here. I'll reopen the file. It's easier to just reopen the file. Let's see, t-test. There it is. Okay, this is t-test templates. Okay, so now this first one is comparing the means of two populations. I'm sorry, yes, on Blackboard. This is called T-Test template for spring of 2015, 2016. Now that you mentioned it, if the one version I have on Blackboard is not exactly the same, let me know and I'll upload this one. I think it is, but I'm not positive. I have so many versions of this. What's it? It should be in the lab data, yeah, in the lab section. T-Test templates. There? It's not there? Okay. Yeah, there's a version of it there, I'm sure. Right? Am I right? No. Yeah, yeah. But like I said, if it's different than this one, I'll upload this one so that we're working with the same thing. Okay, so let's take a look at the situations we might run into. This first one is when we're comparing the means of two populations, two samples, right? Okay, and we're assuming that the standard deviations are equal. That's what we have here. Isn't that the situation we have here? We're going to compare two means. We're going to assume that the standard deviations are equal. What's the next possibility? Well, what about comparing the means of two populations, right? Using samples, two samples, right? Assuming that the standard deviations are not equal. That's the other possibility. And there's formulas to do that. And the third possibility is comparing two population proportions, right? In that case, it always assumes that it always assumes that you're going to use a pooled proportion to calculate your z-score. Okay, in the first two cases, you're going to calculate a t-score, right? Unless you really have a gigantic sample size. In the third case, where it's proportions, you're always going to calculate a z-score because part of your assumptions for doing that analysis is a large sample size. Remember that n times p has to be greater than 5. Okay, so let's take a look at the formulas that we need for this first version of this problem. Okay, so now, since we're assuming that the standard deviations of the two populations, I'm going to blow this up a little bit. It looks like you guys are struggling to see it a little bit. Okay, you can see these formulas. Oops. Okay, so since we're assuming them to be equal, instead of relying on two separate standard deviations, I'm going to put all the numbers together and calculate a single standard deviation, a pooled standard deviation. I'm going to call it SP. SP is going to be equal to the square root of sample size of 1 minus 1 times the standard deviation squared of 1 of group 1 times the sample size of group 2 minus 1 times the standard deviation squared for group 2. Anybody remember what you call the standard deviation squared? Variance, exactly. Remember the standard deviation is the square root of the variance. So that's really the variance, right? But we know we're usually using standard deviation. It's easier to square it. Divide that by n1 plus n2 minus 2, and that gives you the pooled standard deviation. Okay, now using the pooled standard deviation, you're going to calculate what the t-score is. Okay, what is the t-score? It's the difference in the two means of the two populations divided by the standard error. And what is the standard error equal to? It's equal to the pooled standard deviation, which you calculated up here, times the square root of 1 over n plus 1 over n2. Okay, that's going to be your t-score, right? Now, what's the degrees of freedom? The degrees of freedom is just going to be the two sample sizes added together minus 2. Why is the degrees of freedom important to us? Because we're going to calculate a t-score. So we have to know what the degrees of freedom are before we can decide whether or not we exceeded the critical value of t that we need to reject the null hypothesis. Yes?
I'm sorry, the formula here is different than one.
How different is it?
Equal.
What's that?
It's like this.
Oh, look at that. Okay. Let's see. Oh, it's missing. Yeah, hang on a second. S1, S2, pooled standard deviation. That's interesting. Let me see what I got for this. Oh, am I on the right page?
Yes.
Oh, I'm on the right page, yeah. Okay, let me see the other standard deviation. Let me see if I can justify that. Okay, pooled standard deviation times 1. Okay, and down there, I didn't calculate a pooled standard deviation. I'm using the pooled standard deviation. Oh, okay. That's the same formula. Let me explain to you why it's really the same formula. S1 squared and S1's, it really shouldn't be S1. It should be pooled standard deviation squared over N1 plus pooled standard deviation uh, 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 over N2. Those two S1 and S1s down there are really the pool. It should be SP squared and SP squared, both of them. If you factor them out, it's SP squared times 1 over N minus N plus 1 over N, so on and so forth. And now you got SP squared. You can take the square root of it and take it outside of that square root sign. Okay, you guys got it? So it's really, except for the nomen, I know why I changed it on here, because the nomenclature is confusing over there, because we had already used the S, it should have been SP instead of S1, right? So either one, that formula there, if you change the S1, the lowercase s1 to SP, right, then you'll have the same formula in two different forms, right? It's really the same formula. Okay, so I would use this one because it looks a little simpler, right? Because you got to calculate the pooled standard deviation anyway. Yeah, I'll upload. That's what I meant. I have so many versions of this that sometimes gets a little confusing which one I is posted where. Okay, so at any rate, so these are the formulas that I need, right? So we're going to apply these formulas. And once we get done with that, we're going to do the same problem using SPSS to see how much easier it is. Okay, so let's give this a shot. Okay, so let's see. How am I going to calculate that? First, I want to do I want to calculate the pooled standard deviation. Pooled standard deviation. What is the pooled standard deviation going to be equal to? It's going to be equal to the square root. I'm going to see if I can't do this. I'm going to fly without a net and try and do it all in one fell swoop. Okay, you don't have to do that. You could do it in separate cells and put it all together. The square root of n1 minus 1, well, that's 8, right? The sample size, first sample size is 8, right? Times the standard deviation for group 1 squared. What was the standard deviation? It's equal to, the n is 9, right? Right, so n minus 1 is 8. Okay, 8 times the standard deviation for males is 2.73, right? And I'm going to square that, so I'm going to multiply it by that again, right? Okay, plus on top is going to be n2 minus 1, which is 8 again, same sample size as it happens, times, I'll put the parentheses there in a second, times the standard deviation for group 2, which is females squared. Okay, standard deviation is this, times itself is squared. I'm going to put that all together in parentheses. Okay, those are all added together, so I'm going to put them in, I'm going to make sure that they get added together separately, so I'm going to put that all in parentheses, right? And I'm going to divide that whole thing by n1 plus n2, which is 9, and 9 is 18, minus 2 is 16. Divide that by 16. So, okay, you guys ready? I'm going to hit enter here. Let's see how lucky I get. Okay, pooled standard deviation is equal to 0.59. Okay, I'm going to assume for a moment that that's correct. Okay, so what am I going to calculate next? Next, I'm going to calculate my t-score. Yes? Yeah, you would think. Hang on a second. Let me see if I did something wrong there. Did I do something wrong there? Let's see. Pooled standard deviation. Okay, 8. It's going to add these two together. Okay, divided by 16. Oh, you know what it is? I forgot to put the parentheses around here, so it did the square root. It didn't do the square root, but good catch. There it is, 2.3. It is between the two of them. 2.3. What happened there? I forgot. I forgot to put the parentheses around the whole thing. So what it did was it found the square root at the top and divided it by 16, right? Because I forgot to put a parentheses around the whole thing. So it knew to take the square root of the whole formula. Okay. I'm gonna click into it again so you can it's I know for some reason I can increase the size of everything here except the formula that I want to show you. Maybe I can find a way to display that. Okay, space. There it is. You see the formula there? What happened here? The formula here now. Click in there. See now this top part is resolved here, right? And then you need parentheses around the whole thing so that it takes see if I just left it without this parentheses at the end and parentheses at the beginning, it would have found the square root of the top portion of the equation, but not of the denominator, the bottom part of the equation. That's why. So instead of dividing by 16, we're really dividing by 4. Right? That's why the number came out right. But good catch on that. That you're exactly right. Should be between the two. You would think. Right? Depending on how many in each group, it might be closer to one to the other. Okay, so anyway, so now we're going to calculate our t-score. So our t-score, I'm going to resolve, to avoid a problem like that again, I'm going to resolve the top part of it first. And the top part of it's going to be equal to the difference between the two means, which is going to be equal to 10 minus 7.5. Okay, that's equal to 2.4. In the denominator, the bottom part, is going to be equal to my pooled standard deviation times the square root of, let's see, square root of 1 over n, right? What's n? N is 9. Okay, so 1 divided by 9 plus 1 divided by 9. Right? Well, 1 divided by 9 plus 1 divided by 9 is just simply 2 divided by 9. Anybody got a problem with that? Right? As it happens, we lucked out because the sample sizes were the same. If not, it would have been a little bit sloppier, wouldn't it? Okay, so now I'm going to enter. And it turns out that the standard error, which is the bottom part of the equation, is 1.11. So now let's resolve this and find our t-value. Our t-value is equal to the difference between the two means, x bar 1 minus x bar 2, right, divided by the standard error. And my t-score is equal to 2.18. Can I reject my null hypothesis? Well, we got to find out, right? What's the degrees of freedom? Right? Degrees of freedom is equal to n1 plus n2 minus 2. 9, 9, 18 minus 2 is 16. 16 degrees of freedom. I'm going to go back to my table. If I can find it again. Come on, show me my table. Why do these things disappear on me? Okay, let's see. Rusty. I gotta check to make sure. Okay, so 16 degrees of freedom, the t-score I have to exceed is equal to 2.12, right? Okay, did I exceed 2.12? Where was I now? My t-score, where did my t-score go? I lost track of my other file. There it is. Did I exceed 2.12 for my t-score? Yes, I did. So I can reject my null hypothesis and accept my alternative hypothesis. Well, before we finish, we're going to do a problem where we actually lay out the two hypotheses before we do the problem. Okay, that's the calculation I would do if I have equal variances. Let's do exactly the same thing, except do it in SPSS. And I probably should have started a half hour ago when I click SPSS. So it actually starts up in a timely manner. Okay, let's see. Okay, while it's starting up, I'm just going to move on to the next problem just to review it with you. I closed that. No wonder it's coming. I actually did close it. What's that? For the SPSS? I just opened it. Oh, I didn't open a file yet. I was actually, it may be the two sample t-test. I'm not sure if that's the right, is that the right one? Have same numbers? What's that? I was about to cheat anyway, so by just pasting the numbers. But, yeah, yours is going to open a lot faster than mine. No, it's not paired samples. Paired samples is a different one. Remember, paired samples would be males and females can't be paired samples, right? It's got to be the same people before and after, like Fred before and after, Joan before and after. But if it's like if they're next to each other and they're different genders, clearly they can't be this. So it is the paired sample. It is the two sample t-test. Okay, it's just a question of getting the right one because one of them is going to have. What's that? Yeah, if it isn't there, I'm going to just paste it. You'll see me paste it in. I'll show you how you can paste it in. It's just slow starting up for some reason, but it will start up. Okay, so let me go back to the formulas again. So the next situation we might, well, it's starting up. The next situation we might run into is where the standard deviations are not equal. In other words, if we had done this problem and the standard deviation for males had been 4 and the standard deviation for females had been 1, they would have been too far apart for us. So we would have had to assume unequal variances. Now, if you assume unequal variances, the way that you solve this is first you say, okay, t is going to be equal to x bar, this is now not assumed equal, x bar 1 minus x bar 2 divided by the square root of the standard deviation squared for group 1 over the sample size of group 1 plus 1 over the standard plus the standard deviation squared for group 2 over the sample size for group 2. That'll give you your t-score, right? It's kind of a simpler situation. You're not assuming, you're not calculating a pooled standard deviation. You're using this formula for calculating your t-score. The problem now is when you want to calculate what your degrees of freedom are in that situation, you have to use this formula. Okay, kind of a nasty formula, right? Okay, so what I was saying is you can use this formula for degrees of freedom, or you can just simply say whichever one of these is smaller, N1 or N2, just use that number minus 1. And you'll always be working with a degrees of freedom that's smaller than you would calculate with from this formula, a more conservative number of degrees of freedom. Remember, the bigger the degrees of freedom, the smaller the number you have to exceed to reject the null hypothesis. So if you don't want to do that, you could always assume pick the smaller of the two numbers, subtract 1, and say that's my degrees of freedom. Okay? So in case you don't want to do that, SPSS will always calculate t-score. You don't have to worry about it. No matter what the degrees of freedom, it'll apply this formula rather than calculate, not calculate it. Okay, well, is it still bouncing up and down, or what's the story here? Okay, come on. Where are you? Fascinating. I mean, normally computers, they do the same thing every time you do something. I mean, that's how they're designed. So I mean, why this program does something different every time I start it? It's just a fascinating, yeah. There must be some difference that it's seeing. Let me get rid of this. Hopefully, I can get this started up because I really want to show you how you would do this with SPSS because it'll save you lots of work. And again, another reason for using SPSS is that it'll make sure that you don't wind up making errors. Oh, no. Let me minimize that for the moment. Worst case, I can always go over, go over to the PC to do it, which I might actually do at some point here. Close that. We don't need that anymore. Okay, so is it started yet? Is it work? Is it like acting like it might start up? I really have to go online and find out what kind of issue it's got with the version of the operating system I'm running. You guys have similar problems? You guys have Macs? No? Yeah, some of you do. Right? Sometimes it starts up, right? Sometimes it just doesn't. So I don't want to restart because then we'll have to get everybody back online. I see you guys had some sort of connection problem there. Might have been I can never tell whether it's on your end or on my end. But yeah, if it's not everybody, it doesn't happen to everybody, it's probably on your end. It's a miracle. I was really about to just switch over to the PC. Watch it over 4 times now. Where did that go? Yeah, it's opening multiple times. Yeah, multiple files. Okay, so now here is the way that this is laid out. Notice something interesting about this. There are 2 variables, right? It isn't laid out the way I laid it out in Excel with males here and females here. That's the way I would lay it out if I had paired samples. In other words, if number 1 were the same person before and after, I would lay it out that way, right? You see that? So in other words, number 1, that represents one subject. Line number 3 represents another subject. So I can't lay it out male and female because they're not the same person. I could if we were working with paired samples and it were just the same person before and after. And we'll see that in a moment. So instead, I lay out the 2 variables. The first variable, and I'm actually going to go to the variable view and actually put that in. I'm going to call that, what do these numbers look like? Grades. I'm going to call that grade. Okay, whatever that happens to be. Okay. Okay. So the first column is the grade. The second column is the gender. I'm sorry, did I lose you there? The first column is the grade. The second column is the gender. I can go to variable view and I can change the names and so on and so forth. Okay. So I'm going to go back to data view. Okay. So now if I go out, hang on, variable view. I'm going to go back into variable view, and you'll notice that I put down values for this. 1 is equal to male, 2 is equal to female, right? So that SPSS now can identify it for us when it does the calculations. Okay, so go back to my data view. So now I'm going to do my comparison to my means. Okay, and the way I'm going to do that is I'm going to go up to analyze. I'm going to go into compare means. Okay, everybody okay with that? Where I am now? Compare means. Okay, and I'm going to go past means to one sample t-test, past that to independent samples t-test. Not paired samples, not one sample, but independent samples t-test. Okay, it's going to come up and it's going to ask me for the test variable. That's the variable I'm going to find the mean of. That's not going to be gender. I'm not going to find the mean of gender. I'm going to find the mean of the grades. And then I'm going to tell it how I want to factor those, what groups I want to break that up into, which is going to be my grouping variable, which is going to be my gender. Okay, and I'm going to define the groups. Anybody remember, was it 0 and 1 or 1 and 2? 1 and 2. Don't worry, if we get it wrong, it'll tell us. 1 and 2, you have to tell it what the values are that for the 2 groups. I'm going to say okay, and under options, it's already got 95% confidence interval. In other words, that's the same as alpha equals 0.05. If you want alpha to be equal to 0.01, you would make this a 99% confidence interval. Okay, so I'm going to say okay, that's fine. Go ahead and do the analysis. Yes. I clicked OK. I'll go back and do it again. I'm sorry. Let me go back again. Analyze, compare means, independent samples t-test. I put grade into the test variable because that's what I'm finding the means of, and into the gender, into that group, into the grouping variable, I put gender. I want to separate that into the 2 groups. I'm going to define the groups. Now, if you put in 0 and 1, you're going to get it wrong, right? It won't work, right? Because there's no 0. So I put in 1 and 2. I hit continue, okay? And now I check the options. I was okay there. I'm going to hit okay. And it pulls up the output window, and it does the calculation. There it is. It's going to do it again. Okay, let's see what I got for the result. Okay, first thing it did was it gave me a table. Let me blow this up a little bit. No, it's not going to work. Okay, gave me a table. So see, sample size is 9 for each group. The mean is 10 and 7.56. The standard deviation is 2.79 and 1.944. That's the same numbers we got before, right? When we did it by hand. Okay, so let's go down to our independent samples t-test down here in the second box. Okay, first thing you see is this set of 4 boxes here. Levine's test for the equality of variances, right? Okay, now the way I look at this, the way I rationalize this is whenever we do a statistical, almost always when we do a statistical test, we start with a null hypothesis that 2 things are the same. In this case, the 2 things we're talking about are the variances. So I'm going to assume that we have equal variances. And unless my statistical result for that test, testing whether or not they're equal, my statistical result, my significance or p-value is less than 0.05, I'm not going to reject that idea that they're the same, right? As long as my significance or p-value is not less than 0.05, right? I'm not going to reject the idea that the variances are equal. But if that value significance is less than 0.05, I'm rejecting the idea that the variances are equal and saying that I'm assuming that the variances are not equal. Now, if the variances are equal, in this case, it's not less than 0.05, so I'm going to stick with that. I'm going to use the top row. If the variances are not equal, I'm going to use the bottom row. In other words, if this is less than 0.05, I use the bottom row. If it's not less than 0.05, I stay with the top row. I use that as a justification to drop down to the bottom row. Okay, let's see what we wound up with here. Now we're going to use the top row. I don't need this test anymore. That was just to decide whether I'm going to use the formulas for equal variances or unequal variances. Now that I've decided that, I just go across the top, and the t-value that I calculate is 2.184. Bless you, by the way. 2.184. Same number that we found before, right? Or pretty much same number. The degrees of freedom is 16, same one that we used. The significance, the probability of being wrong if we reject the null hypothesis, the area of the tails at either end where that t distribution, when you add the 2 tails up, is 0.044, which is less than 0.05. Since this is less than 0.05, what can we say about our hypothesis? We reject the null hypothesis, right? It's less than 0.05. That's a justification for saying the 2 means are different. Remember, the null hypothesis, 2 means are the same. So we reject the null hypothesis and we accept the alternative hypothesis. Had the significance been bigger than 0.05, we would have said we failed to reject the null hypothesis. We don't say we accept the null hypothesis. We don't know if it's true. All we know is we failed to reject it. Okay? So don't ever anybody ask me, what do you do when it's exactly 0.05? Everybody asks me that every semester. I don't think there's an answer to that question. What can I tell you? Don't there's anybody ever read a book called Catch 22? Did you read Joseph Heller? It was an immensely popular novel in the past century. When I went to college. It's about World War II, and it's about these fighter pilots in World War II, right? And they would have to go out on these missions, and they had enormous casualties and stuff like that. So they always wanted to avoid the missions. But there's all catch-22s, all things in the typical of the Army that when you get to they don't seem to make much rational sense. And one of them was that if you wanted to go on sick call, not go on a mission that day, you had to go to the medical tent, and they took your temperature, right? And the rule was if your temperature was over 102, you were on sick call. If your temperature was under 102, you had to go on the mission, right? So if you would go over there and your temperature was measured, and it came out 102, no one knew what to do, right? So it's the same deal with a p-value 0.05, right? So there really isn't a good answer to that. It's at any rate, yeah, okay. The significance, this 0.245 is only for the is only part of this block of four over here, where you're using it to determine, it's not actually your t-test, but you're using it to determine whether you should assume equal variances and use the top line, or whether to use unequal variances and use the bottom line. That's the only thing that you're using it for. Once you've made that decision, like in this case, it's greater than 0.05, so we don't reject the equal variances, so we stick with the top line. Okay, if it had been less than 0.05, we would have used the bottom line. Now the rest of this over here is our t-test. Our t-test came out to be 2.184. Degrees of freedom came out to be 16. Now normally what we would do is we would go to our t-table and look up to see if that t-score, with that number of degrees of freedom, if that t-score was bigger than the critical value of t. If it's bigger than the critical value of t, I think we decided before that it was like 2.1 or something like that. So what was bigger? So we could reject the null hypothesis. Well, in this case, you can even go further than that. SPSS actually calculates a probability of being wrong if you reject the null hypothesis. And that's two-tailed. In reality, if you just looked at the t-score and you said to yourself, oh, this number is bigger than that number, so it's all the way over here in the tail. And the area to the right of that is only 2.2%, right? Well, the problem is that's nice, but you didn't know it was going to be on that end when you started. It could have just easily been on the other end. So you have to account for both ends. So when you do two-tail test, you're going to take that 2.2% and you're going to double it to get the overall two-tailed significance, which is 0.044. But it's still under 0.05, so you can reject the null hypothesis. Okay, so how are you guys online doing? Okay, you guys okay online? You following this? Okay, good. So now let's go back and let's try another example of this. Okay, so now since we're a little bit pressed for time, I'm not gonna do the version of it in Excel, which is a unequal variances. The only difference is you're using different formulas, right? When you do that, I'll do it in SPSS, however. So I'm going to go into SPSS. I'm going to open up this version that says two sample t-test. Is there another sample? Another one here? Is this different? Let me see if that's different. No, it's the same thing. Same. I'm not going to bother. I'm not going to bother with it. I'm going to go instead to paired samples t-test. Okay, so now here's an example of a paired samples t-test. Okay, and maybe I don't know what these are. Maybe they represent pain levels, or pain level 14 is pretty bad, right? So maybe they represent some metabolic function or something like that. And you've taken people and you've tried them for 2 weeks on a placebo and 2 weeks on a drug, and measured them at the end of each 2 week period. Some of the people, now how many people are in this study? 9, not 18, 9, because these lines represent the same people, right? So there's 9 people in this study. Some of these people, you don't see it here the way the data is laid out. Placebo and exactly, because that's the idea of a paired sample t-test. You don't want to compare people, because you could have people take the placebo, a lot of them could be smokers, and the people take the drug, a lot of them might not be smokers. This way you get to look at the change only for each person. So that person could be overweight before and overweight after. So you kind of control for variables better that way, right? So now let's take a look at this. Now, each one of these is a single person. Now, keep in mind that you don't see it here, but it's likely in most of these, you randomize what order that they received the treatment. In other words, person number 4 might have gotten the placebo first and the drug the second 2 weeks, and person number 5 might have gotten the drug the first 2 weeks and the placebo. Can't see that here because of the way the data is organized, but you often randomize the order of the treatment if you're comparing two of them. So what am I really looking at here? I'm really looking at a difference. What's the difference between the placebo and the drug? Well, it's equal to the placebo minus the drug, let's say, right? It's equal to 0 for that person. But for the rest of them, it's equal to all sorts of different changes. So if there's no difference between the placebo, the effect of the placebo, and the effect of the drug, what would we expect the average difference to be? 0. We would expect it to be 0. So what's our null hypothesis? Our null hypothesis is that mu of the difference, the mean difference, is equal to 0. What's our alternative hypothesis? Mu difference not equal to 0. Now, have we predicted ahead of time whether or not, do we have any information for sure whether or not this number is going to be higher or lower for the placebo or the drug? We don't know, right? So this is going to be a two-tailed test. If you could tell me metabolically that this drug can only lower blood pressure, can't possibly raise it, then you might consider doing a one-tailed test, in which case you can have all 5% on the right-hand side, okay? Which means your t-value can be smaller and still reject the null hypothesis, okay? So now let's actually go ahead and do this analysis. I think we have, so now in order to do this, what is this? Now this is a one sample t-test, right? All you're doing is comparing whatever the mean of this group is. The mean is equal to average. Here's the mean of the differences. Is that, and the standard deviation of the differences. Is equal to this. Oops. This, and now we can compare, now we can calculate standard error and so on and so forth. And it's basically like doing a one sample t-test, except the mean you're comparing it to is 0. Okay, so now I'm going to use SPSS, okay, and the way you would do that again is the difference between, is the 1.5 minus 0, right, divided by the standard error, which is the standard deviation divided by the square root of the sample size, right, and so on and so forth. So now, and that would give you a t-score, and then you would check it against the t-table. So now instead, I'm going to do this in Excel, I hope. Right? Let me see if I can't find the one that is. Now, you're going to notice that there's a difference in the layout here. Paired samples. Come on. Is it open already? Is it open already? Two sample. Nope. Don't need that one anymore. Come on, open up. We try it this way. Open, data. Okay, desktop. Oh, wait, I think I'm there already. Open. Oh, did I open the wrong one? Okay, great. Oh, now nothing's happened. Oh, there it goes. Okay, I didn't want this one. Open. See, I was talking about single sample. The similarity between the single sample, paired samples. I guess it just doesn't like that file. Oh, there it comes. Okay, so I'm assuming that these numbers are correct, that it's the same numbers that we were working with before. Okay, so now here's placebo and drug, except this is subject 1, subject 2, subject 3. So how do I analyze this one? Analyze descriptive statistics and and I'm sorry, means, compare means, and having seen a moment here, paired samples t-test, yeah. Okay, so we bring that up, should be simple enough. Now notice there, because we're looking for two sets of numbers, two variables, it requires me to put in both. First, I'm going to put in the placebo, right? But that's not enough. Now we need something to pair it with. Then I'm going to put in the drug result. Okay, now that that's in, it gives me the okay, and I can go ahead and do that. In options, again, all you have to, or you can define what your alpha error is or your level of confidence is by changing that 95%. And I'm going to click OK. Okay. So there's no question of equal variances or unequal variances because there's only one variance. There's only one sample involved. Really, even though there's two sample results involved, there's really only one set of numbers that you're working with, and as a consequence, you only get a single line in your output for paired samples t-test. And what do we get? Mean 1.556, the same as we got in Excel. The standard deviation, the standard error, the confidence interval is calculated also. I'll talk about that in a second. And the t-score is 1.73. Does that sound like a t-score you can reject a null hypothesis with? No, it doesn't sound too good, right? Usually it's got to be over 2. Degrees of freedom are equal to 8, and the two-tailed significance is 0.12, right? Not less than 0.05. So all of that tells me I can't reject the null hypothesis. Well, how about the confidence interval? The confidence interval is -5 to 3.6. Now remember that we're trying to say that the mean for the differences is different than 0. And we're 95% sure that the mean for our differences is between -0.5 and plus 3.6. So 0 is in between there. I can't say that it's different than 0 because 0 is inside my confidence interval. If we're outside my confidence interval, I could say that I'm not better than 95% sure that the mean for my sample differences is different than 0, right? But since it's inside that confidence interval, just like with the significance being greater than 0.5, I can't reject the null hypothesis. Okay, one more look now. The last thing that we really should look at is proportions. How are proportions different? Well, again, in proportions, your point estimate, remember she says point estimate quite a bit. Your point estimate is just another way of saying the middle or the average or the proportion. Okay. In when you're dealing with proportions, your point estimates that you're comparing are not your means, they're your proportions. 20% of this group got diabetes, 18% of this group got diabetes. Those are your point estimates. But you use them just like you use the mean. Okay. So we're going to go over here to, okay, let's see. We're going to go over here to my table chart here. Oh, here we go. Okay, how do we deal with proportions? Okay, comparing the proportions of two populations. Okay, now the sample sizes, the rules I've heard in the past is that you want a sample size of at least 30 total with 15 in each outcome. Well, this kind of, let's see if this works for, it may not work for I'm not sure. Did I have an example of that? Proportions? I don't see one there, do I? I don't see one. Okay, I'm not going to worry about it actually, I'll tell you where we can do this. I'm going to open up a data file that we already have. So now, let's say I have a situation where 20% of one population, I take a sample of population A, and I find that 20 out of 100 people are diabetic. I take a sample from population B, and I find 15 out of 100 people are diabetic. Are my sample sizes big enough? So now my n times p, my sample size is 100, times my probability of being diabetic, which is 0.2, is 2. That's 20. That's bigger than 5. On this other group, 15 out of 100, my sample size n is 100, my proportion is 0.15. That's 15. That's bigger than 5. So I can do this t-test or difference of proportions or proportions. So now I'm going to start with that presumption that I have 20% here, 20% here. Now, how am I going to resolve this if I do it by hand? Well, the first thing I need is to calculate a pooled p-value, right? A pooled proportion. P1 is 20%. N1 is 100 people. P2 is 15%. N2 is 100 people divided by 100 plus 100, 200 people. My pooled proportion is just simply 20 people. Remember, it's 20 out of 100. It's just 20 and 15, 35 out of 200, right? It's just the average of the two of them. If it's the sample sizes are both the same, it's just the average of the two proportions. It's actually the weighted average, because if the sample sizes were different, this would kind of give you a weighted average. But now my p-value is actually 35% divided by 2 would be 17.5%, 0.175 is my pooled p-value. Okay, so now let's calculate the value for z. Now we're using z here. How would we calculate it for this test? It would be population 1 was 20%, 0.2, minus population 2 is 15%, which would be 0.15. So the difference is 0.05 on top. And what's on the bottom? My standard error. And how do I calculate? The square root of not P1 or P2, but the pool standard proportion, which is 0.175 times 0.825 times 1 over 100 plus 1 over 100, which is 2 over, which is 1 over 50, I guess, right? 2 over 100, 1 over 50. Find the square root of the whole thing, divide that into the difference between the two proportions. And let's say, for argument's sake, why don't we actually calculate this? Just for the hell of it, for the example I just described. Okay, it's going to be on top, it's going to be 0.05. On bottom, it's going to be equal to the square root of 0.175 times 0.825, 1 minus that. Okay, and that's going to be multiplied by 1 over 2, 1 over 50. It's going to be 1 over 100 plus 1 over 2 over 50. A point is 0.02, right? 0.02, right? Times 0.02. Times 0.02. And I'm going to take square root of the whole thing, not just that. Okay, I've got to put another parentheses here. Okay, and that's divide, and that's multiplied by. Okay, good. So let me see if I get something here. So it's my standard error is equal to 0.053. So my t-score is going to be equal to p1 minus p2 divided by my standard error, which is it's just not, which is 0.93, right? And really, that tells me the area to the right of where I want to be. So it's really equal to 1 minus 0.93, which is 0.069, and that's only one tail. I still got to double that for the other tail. So it's like 4 point, my significance, two-tail significance is like 14%, 0.14. Sounds a little complicated. When you practice it a little bit, you'll see, you'll get used to applying, recognizing what your situation is and applying these formulas. Okay. Does that make sense? Did I make a mistake on this, by the way? Did you get the same answer I did? What's that? Okay, good. I'm glad to hear it. So I want to check, because when I'm doing this and I'm trying to describe it and do it at the same time, it gets a little complicated. So that's the way that we would deal. Now, keep in mind that in all of these cases, right, in all of these cases, I'm not touching a thing. Okay. I don't know why it's doing that now. It's amazing. You know, it's whenever you get this software that is frequently updated for reasons. It's frequently updated for reasons because the science changes, the math changes, there's developments, new tests that people use. So they do frequent updates. And the problem is that when it's vertical software, where instead of a program like Microsoft Word, where 1 billion people in the world are using it, it's a program where there might be 70,000 people using it. The updates are a little bit buggier. It takes them a little bit longer to get it straight, and so on and so forth. There's less money that goes into and less availability of talent to actually do this. So at any rate, I just wanted to point out one more thing here, and it's we're just about at the point where we should quit. What I'm going to do is I'll set up a session on Wednesday night, maybe like 9, 10 o'clock, where I will go through some of the remaining problems on this exercise, particularly the ones as you look through those pages on this document, you'll notice that the ones towards the end, I actually ask you, what's your null hypothesis? What's your alternative hypothesis? So you have to go through it step by step, right? So keep in mind that one of the deals that you have here is that as you go through this, that, for instance, instead of just looking at these numbers, that in reality, you have to answer questions about this, right? You have to go through a certain procedure. Okay, and let me see if I can find them. Okay, let's see. For instance, here, state your null and alternative hypothesis. Calculate your standard error. Okay, calculate the appropriate statistics, Z or T. In other words, you go through this whole sequence of events. The first thing should be your statement of your null and alternative hypothesis, right? Always, okay? And stating it correctly. So that, but we'll get a chance. We'll exercise that a little bit. So now this is what we learned tonight. We learned how to deal with two samples. Next week, I'm not sure what the schedule has for next week. I think it's analysis of variance. I could be wrong. It's either going to be chi-square, which you got a little teeny tiny taste of here. Another kind of test, another kind of statistical test where instead of comparing uh, 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 means, you're comparing tabular data. For instance, if you accumulated data, remember what your boxes look like for the diagnostic tests. Like in other words, if it's a positive test, how many people had the disease and so on. Well, this time it's going to be if you have an exposure to say nickel, or if you don't have an exposure to say nickel in the rows, exposure or no exposure, and in the columns, how many people got a disease like nasal pharyngeal cancer, right, in one column, and how many didn't. So you have a box of four numbers. How to determine if there's an association between the exposure and getting the disease or not. That's what you would use chi-square for. The following week, or switched around, we would be looking at analysis of variance. How to tell whether two groups are different based on the variability of the two groups. So that's kind of an interesting idea, telling whether they're different based on variabilities rather than just on simply the mean, right? So we're going to be looking at that as well. So we're going to be looking at a lot of tests now. Then we're going to be looking at correlation. How about if you have two numerical variables like what your BMI is and what your blood sugar is, right? Both of those are numerical variables, and a person has both a BMI and a blood sugar level. Well, how can you tell whether or not there's an association between those two? That's called correlation. And there's a technique that we use that's called regression, where we can quantify the idea of what is that association? How strong an association is it? And can I quantify it so I can use it to predict, whether a person would have a high blood sugar based on their BMI and so on. So we're going to be getting into some really interesting stuff from this point on. Okay, now I'm not sure what's the deal on the project now. You've submitted, I think the last thing we did was you submitted some basic descriptive statistics, and I'll have to go into Blackboard. I don't know what the next step, what the next milestone. Yeah, is there a milestone coming up? Is there like the 15th of May? That's like the end of the semester, you're saying. But there must be another milestone somewhere, right? Yeah, I'll check it out. I'll check with Professor Waika and see if there are other milestones in between. It's always nice to be able to get some feedback, as you go forward.
I think the next thing you should study is descriptive statistics.
Okay.
Descriptive statistics.
Yeah. Oh, I think you did some already, right? Didn't you already submit some descriptive statistics? Yeah. Yeah. Okay. I'll check with her and find out what the next milestone is. Okay. That way we can start maybe kind of keep up with each other. Okay, guys, online. Good night. I hope this was okay. I didn't see too many questions tonight from you guys. Yep. The lab recording from tonight. Yeah, no problem. As soon as I get home, I'll get it together and post it. And I'll see you guys next week. Good night.